Proving problems are PSPACE complete. When we studied NP, we had to prove a first problem NP completed directly from the definition of NP. After Cook and Levin did this for satisfiability, many other NP completed problems could follow by reduction. A similar sequence of events followed for PSPACE, shortly after the results for NP. Recall that we defined PSPACE completeness by directly analogy with NP completeness in section 9.1. The natural analog of circuit satisfiability and 3-set for PSPACE is played by Q-set, and Stockmayer and Mayer, 1973, prove that. 9.9 Q-set is PSPACE complete. This basic PSPACE complete problem can then serve as a good route from which to discover other PSPACE complete problems. By strict analogy with the case of NP, it's easy to see from the definition that if a problem Y is a PSPACE complete and a problem X in PSPACE has the property that Y is polynomially reducible to X, then X is a PSPACE complete as well. Our goal in this section is to show an example of such a PSPACE completeness proof for the case of the competitive facility location problem. We will do this by reducing Q-set to competitive facility location. In addition to establishing the hardness of a competitive facility location, the reduction also gives a sense for how one goes about showing PSPACE completeness results for games in general based on their close relationship to quantifiers. We note that planning can also be shown to be PSPACE completed by a reduction from Q-set, but we will not go through that proof here. Relating quantifiers and games. It is actually not surprising at all that there should be a close relation between quantifiers and games. Indeed, we could have equivalently defined Q-set as the problem of deciding whether the first player has a forced win in the following competitive 3-set game. Suppose we fixed a formula phi of x1, x2, x3, and so on until xn consisting, as in Q-set, of a conjunction of length 3 clauses. Two players just alternate turns picking values for variables. The first player picks the value of x1, then the second player picks the value of x2, then the first player picks the value of x3, and so on. We will say that the first player wins if phi of x1, x2, x3, and so on to xn ends up evaluating to 1, and the second player wins if it ends up evaluating to 0. When does the first player have a forced win in this game, i.e. when does our instance of competitive 3-set have a yes answer? Precisely when there is a choice for x1 so that for all choices of x2 there is a choice for x3 so that, and so on, resulting in a phi of x1, x2, x3 until xn, evaluating to 1. That is that the first player has a forced win if and only if, assuming n is an odd number, there exists x1 for all x2, there exists x3 for all x4, and so on. There exists xn minus 2 for all xn minus 1. There exists xn such that the phi of x1, x2, x3 until xn holds or not. In other words, our competitive 3-set game is directly equivalent to the instance of Q-set divided by the same Boolean formula phi. And so we have proved the following. 9.10 Q-set is polynomially reducible to competitive 3-set, and the competitive 3-set is polynomially reducible to Q-set. Now proving competitive facility location is PSPACE complete. Statement 9.10 moves us into the world of games. We use this connection to establish the PSPACE completeness of competitive facility location. 9.11 Competitive facility location is a PSPACE complete. Proof. We have already shown that competitive facility location is in PSPACE. To prove it is a PSPACE complete, we now show that competitive 3-set is polynomially reducible to competitive facility location. Combined with the fact that Q-set is polynomially reducible to competitive 3-set, this will show that Q-set is polynomially reducible to competitive facility location, and hence will establish the PSPACE completeness result. we are given an instance of competitive 3 set defined by a formula phi. Phi is the conjunction of clauses C1, which is intersect C2, which is meet C3, meet C4, and so on, meet CK. Each Cj has length 3 and can be written as Cj equals to Tj1 join Tj2 join Tj3. As before, we will assume that there is an odd number n of variables. We will also assume quite naturally that no clause contains both a term and its negation. After all, such a clause would be automatically satisfied by any truth assignment. We must show how to encode this Boolean structure in the graph that underlies competitive facility location. We can picture the instance of competitive 3 set as follows. The players alternately select the values in the truth assignment, beginning and ending with player 1. At the end, player 2 has won if she can select a clause Cj in which none of the terms has set to 1. Player 1 has won if player 2 cannot do this. It is this notion that we would like to encode in an instance of competitive facility location, that the players alternately make a fixed number of moves in a highly constrained fashion, and then there is a final chance by player 2 to win the whole thing. But in its general form, competitive facility location looks much more wide open than this. Whereas the players in competitive 3 set must set one variable at a time. In order, the players in competitive facility location can jump all over the graph, choosing nodes wherever they want. Our fundamental trick then will be to use the values bi on the nodes to tightly constrain where the players can move under any reasonable strategy. In other words, we will set things up so that if either of the players deviates from a particular narrow course, he or she will lose instantly. As with our more complicated NP completeness reductions in Chapter 8, the construction will have gadgets to represent assignments to the variables, and further, gadgets to represent the clauses. Here is how we encode the variables. For each variable xi, we define two nodes vi, vi prime in the graph G, and includes an edge vi, vi prime, as in figure 9.2. Selecting vi will represent setting xi equals to 1. Selecting vi prime will represent xi equals to 0. The constraint that the chosen variables must form an independent set naturally prevents both vi and vi prime from being chosen. At this point, we do not define any other edges. How do we get the players to set the variables in order? First x1, then x2, and so forth. We place values on v1 and v1 prime so high that player 1 will lose instantly if he does not choose them. We place somewhat lower values on v2 and v2 prime and continue in this way. Specifically, for a value c which is greater than or equals to k plus 2, we defined the node values bvi and bvi prime to be c to the 1 plus and minus I. We defined the bound that player 2 is trying to achieve to be b, the bound, equals to c to the n minus 1 plus c to the n minus 3 and so on plus c to the 2 plus 1. Let's pause before worrying about the clauses to consider the game played on this graph. In the opening move of the game, player 1 must select one of v1 or v1 prime, thereby obliterating the other one. For if not, then player 2 will immediately select one of them on her next move, winning instantly. Similarly, in the second move of the game, player 2 must select one of v2 or v2 prime, for otherwise player 1 will select one on his next move. And then, even if player 2 acquired all the remaining nodes in the graph, she would not be able to meet the bound b. Continuing by induction in this way, we see that to avoid an immediate loss, the player making the ith move must select one of vi or vi prime. Note that our choice of node values has achieved precisely what we wanted. The players must set the variables in order. And what is the outcome on this graph? Player 2 ends up with a total of value of c to the n minus 1 plus c to the n minus 3 and so on plus c to the 2, which is equals to the bound b minus 1. She has lost by 1 unit. We now complete the analogy with a competitive 3 set by giving player 2 one final move on which she can try to win. For each clause Cj, we define a node Cj with the value b Cj equals to 1 and an age associated with each of its terms as follows. If t is equals to xi, we add an h Cj vi. If t is equals to xi bar, we add an h Cj vi prime. In other words, we join Cj to the node that represents the term t. This now defines the full graph G. We can verify that because their values are so small, the addition of the close nodes did not change the property that the players will begin by selecting the variables nodes vi, vi prime, the pair, in the correct order. However, after this is done, player 2 will win if and only if she can select a closed node Cj that is not adjacent to any selected variable node. In other words, if and only if the truth assignment defined alternately by the players failed to satisfy some clause. Thus, player 2 can win the competitive facility location instance we have defined if and only if she can win the original competitive 3 set instance. So the reduction is complete.